Hello, friends. So, let us start with the next topic, that is torsion. Torsion, actually, we can define it as a force that twists something is called a torsion. Torsion occurs when an object, such as a bar with a cylindrical or the square cross section, is twisted. Let's say if this is a marker and we are just trying to twist this from this part, okay, like this, we are twisting this. So this you can consider as a torsion if it is a cylindrical bar or a square cross section. So to understand that this term or this so let us consider a circular shaft or a beam of length L. So if here we may consider cantilever. Cantilever is basically what it is, a beam with one end fixed. So this end is fixed. If this is a circular beam like this, we can consider. So this part we may consider as the length of this beam is L, and here if this is the centroidal axis, and as we will twist, we will apply some twist here in this direction like this. If we will twist, so some part or some fiber of this will be twisted by an angle. Let's say it's phi. Let's say it's phi is the angle between this portion, like if it is q, so it is q dash. So in the figure you can say, if this is t, t is the torque or the moment applied in this angle like this, that is phi we have considered here. So let's say if the cross section of this part, the cross section of this part, we can say the front view of the beam. So if we will draw this separate figure, if the beam is the circular beam and here this point q is here, and it will be up to the center. If the center is o, and after the t torque that is applied, or the moment after this particular moment we have applied, so then uh, here it will be in the circle, because this end is fixed but this end is not fixed. So as I told you that we are taking an cantilever type of the beam. So here this will be q dash, we can say here. So if r is the radius, so if at this particular end, if the angle that will be theta, so let q dash q dash, uh, it is in fiber, we have considered it as a fiber. If this we have considered as the centroidal axis or the neutral axis, we can say here, of the beam, so then we can find out the shear, angle of shear or the shear strain. So what will be the shear strain? So if in this case we may consider, so that is phi. So phi is equals what, this is q dash over the distance or the length L. So we can say q dash, that is equals to phi L or L phi. So this is our equation number 1. In the same similarly we can find out in this circle here. So this is the angle at the fixed end of this cantilever, and for this particular cross section at the front view we will see that there is some different twist. So here in this figure we can find out the value of this q dash, and in the cross sectional view, if angle is theta, then q dash that is equals to r theta. Okay, equation number 2. So from equation 1 and 2 we can say that L phi is equals r theta, or the phi value of this phi also we can find out in terms of this. So that is r theta upon L. L is the length of this beam. So we know the modulus of rigidity. So that is equals to shear stress upon shear strain. So if we will represent this shear stress by tau and shear strain that is phi, here the angle of shear we have represented. So let me erase this and need to put the value of this phi here. And if the modulus of rigidity is represented by n, then we can say, so either by this here in this equation, so we can say phi is equals tau by n. So we can also put this value here in this equation. So what exactly the term will be? It is L into, in place of phi we will put tau by n, that is equals to r theta. Okay, so now this will be the by this equation, if we want to find out the maximum shear stress, the value of tau we can find out by this equation. So the tau maximum that can be written as it is r theta, this end will be here and L is like this. So this is our equation number 2, and we can say it's 3, and it's equation number 4. Okay, so let me raise this and need to discuss further. Okay, so finally tau maximum, so this value we have n r theta over L. This is our equation number 3rd or 4th, I think so. It was 4th. Now let us consider, let me draw the circle again. We need this circle. So if this was the central point and this is another inner circle, if this is I think we can say it's q dash, and here it is q, we have considered theta, the angle between that, and if r is the radius from the central point O, and this for if we will consider a small segment, small part here, like this is a small part, we can say it's del A, the area of that is, and it is at a distance small r. Okay, at a distance small r this is. So we can say the value of this tau r for this small part that can be this was the maximum value of the shear stress we have find out. And now for this small segment, if we want to find out, so that will also be equals to this sum. We can say it's n r theta over l. So this is our equation number 5. So the shear stress is equals to the shear force upon area. Okay, so by this, what is the shear stress? That is our tau r, and that is equals to shear force, we can say SFR for this small part now we are discussing, and upon delta A is the area of this small part or the region. So the shear force, so that is equals to, where by this equation we can say it's tau r into del A. So what is tau r? So by putting the value from equation number 5 of tau r, so we will have n, for here it is small r for this particular reason. For tau maximum at this point, that is capital R. Okay, so now we can say it is n r theta upon L into delta A. So we know that the torque capital T, we can represent it by capital T, so that is equals to the shear force into perpendicular distance. So what is the perpendicular distance? So that is simply the r, and if we will put the value of shear force from this equation, so here we can put the value of n r theta upon L delta A into again this distance r, perpendicular distance from the centroidal axis or the neutral axis, we can see. Okay, so what exactly the shear force is now? We can write it as, so from this equation, so we can say uh, T shear force. Okay, so that is equals to what? It is n, from this equation we can write simply n theta upon L delta A into r square. This r into this r, that is r square. Like this we can write it. So the torque on the circular shaft can be written as, if we want to find out the torque on that circular shaft from the from this point, we can say from O to this region R. So from this value R is equals, that is our small r. So here it is small r. So from r is equals 0 to capital R, if we will integrate this sum, so we will have like it's 0 to r and n theta or L delta A r square dr. Okay, so by the integration of this sum, or we can say, we know that the in polar coordinate the moment of inertia that is simply jp. So we can say here it is t is equals, this sum we will write n theta over L into the rest of the term can be written as it is jp. Okay, so this is, I think, equation number 6 now. Okay, and where this jp is what? Jp is the moment of inertia at polar coordinate. Okay, so like this we can represent this term as, if this jp is just about in the denominator of this t, so we can write is t over jp, that is equals to n theta upon l. Okay, so this is our equation number 7. Okay, and as we know that uh, tau upon r, tau upon r by the previous discussion in my last slide here, so that can be written as n theta over l. So this is equation number 8. So by this equation 8 and equation 7 we can write, that t over jp is equals tau by r is equals n theta upon l. So this is the required relation between these variables.